Section 7.1, Rational Expressions, specifically multiplication and division. So in Chapter 7, we're going to look at rational expressions, which are really just kind of these crazy-looking fractions that have polynomials in the top and bottom. And what we're going to be doing with these fractions, with these rational expressions, will require us to know how to factor. So the stuff we just talked about, learned in Chapter 6, is going to definitely come into play in all of these sections. So rational expressions, in general, we can say they're made up of the set of two polynomials, the ratio of two polynomials. So taking a polynomial p over some polynomial q. As long as, with any fraction, the denominator, in this case whatever's on the bottom, the q value, that polynomial cannot be equal to 0. In math, we cannot divide by 0, it's undefined. Therefore, a fraction can't have a 0 in the denominator. Okay, so that's one thing to consider, specifically when we're trying to find what is called the domain of the polynomial. Okay. Our denominators of these rational expressions we cannot allow to equal 0. So if you recall, at some point we talked about domain is the set of all possible x values. Okay. So if we're going to look at all the possible x values we could plug into a function, everything is going to be good except for those x values that make the denominator equal 0. So in our first set of examples here, we're trying to find the domain. So it's asking us to look at this function and determine what x values are okay to plug into it. So in this first example, we have f of x equals 2 over x minus 5. So this is pretty much telling us that if we take the denominator and we can say, well, x minus 5, we want to figure out what value is going to make that equal 0. And whatever value does that, we're going to say x cannot be that. So I like to write it as x minus 5 cannot equal 0 rather than equal 0. So if we were to solve this for x, we would add 5 to both sides of the equation. And this would give us that x cannot equal positive 5. That's the one x value that we're not allowed to take. And you'll see my math lab will write this sometimes in set builder notation. It'll be the set of all x values, then this line, meaning such that x cannot be equal to 5. So it can be the set of all other possible x values. X can be any number other than 5. Okay. And it can be any number except 5, because 5 is the one value if we plug in for x will give us a 0 here. 5 minus 5 would give us 0 in the denominator. Okay. So our next example, we have the expression, the function 3x over 7x minus 14. This is another what we call rational expression. We have a fraction that has a polynomial top and bottom. Doesn't matter what would make a 0 in the numerator. All that matters is what would make a 0 in the denominator. So we look at the denominator, 7x minus 14. And once again, we say that we're not allowed to let that be equal to 0. So we need to solve this equation for x, adding 14 to both sides of this non-equation would give us 7x cannot be equal to positive 14. And then dividing on both sides by 2 gives us that the domain divided by 7 on both sides, x cannot be equal to 2. Okay. Once again, if it's written in set builder notation, it will be the set of all x's such that x cannot equal 2. Okay. So we're good with x being any other number except for 2. So now we have a new, part C here, we have a new rational expression, a rational function, 6 plus x over x squared minus 4x plus 3. Well, continuing with this idea that we've been following so far, we are not allowed to let our denominator be equal to 0. So x squared minus 4x plus 3 is not allowed to equal 0. As long as we take x values that don't do that, then we're okay. But this is a little harder to find out what x values will make that denominator equal 0, because it has an x squared in it. Well, we've just been learning in our last few sections how to factor and how to solve an equation that's set equal to 0 by factoring. So that's what we're going to want to do here. We need a factor, and then that is going to let us know the two x values that would make this equation equal 0. So how we do that? We try to find the two numbers that add to give us negative 4. Again, adding to give this middle term negative 4, and they have to multiply to give us the number on the end, the 3. Okay? It's as simple as that, again, because x squared doesn't have a coefficient out front. So the two numbers that will do this are going to be negative 3 and negative 1. If we add these, it will give us a negative 4. If we multiply them, it'll give us the positive 3 we want. Okay. So that means the left side of that will factor into x minus 3 and x minus 1. Again, we can think of it as can't equal 0. Okay, because whatever numbers we find from here that will equal 0 are going to be numbers we do not include. Okay. So just from looking at that, we can see what value is going to give us a 0 here. Well, 3. And what value here would give us a 0, 1. Or if you need to, set it up as your two equations. X minus 3 can't equal 0, and we cannot let x minus 1 equal 0 either. And then solving those two, adding 3 to both sides, we get x can't equal 3, or x cannot equal 1 if we add 1 to both sides here. Okay. So I'd be fine you writing it like that on a test, although I think on my math lab they might have you write the domain this way again. Set of all x values such that x does not equal both 1 and 3. And then close that bracket. So this way or this way means the same thing. Okay. Got two more expressions to look at. Our next rational expression, our next rational function is 8x plus 2 over 3. So again, we're trying to find what x value, if we plug it in, will give us a 0 in the denominator. And once we find that x value, we say that's not part of our domain. But because there is no x in the denominator, it's just a 3, and it will always be 3. So there's no x to make it turn into any other number. And so it will never be 0. So our domain is everything. All real numbers is how we describe that. So let's get that down in words. Since there is no x in the denominator, so it always equals 3. And more importantly, that denominator will never equal 0. So we write that our domain is going to be all real numbers. And another way to write that mathematically is in interval notation. If you remember, we wrote it as negative infinity to positive infinity would be our domain. Okay. And then our last example, Okay, looks like we have an expression. It does have an x, so there is, looks like something we could find that would make that denominator equal 0. So again, let's take the denominator, x squared plus 4. And as usual, we're going to say we cannot allow this to be 0 when we're trying to find our domain. So I guess what we've learned so far, when we have an expression like that, we want to factor when it has the x squared in it. So we want to look at that and try to factor it. However, it looks like it's those both are squares. We have x squared and 4 is a perfect square, is 2 squared. But it's the sum of those two. We're adding them. That is going to be something that can't factor. Okay, it's not factorable. It's prime. So instead, we could kind of try to do what we did up here, move things around. Okay, we could move the 4 to the other side of the equation to try to subtract it from both sides. Doing that is going to give us that x squared cannot equal a negative 4. And then if you think about this mathematically, what number when we square it will give us a negative 4? And if you really think about that, then you find that there is no x value that's going to do this. Anytime you square a number, if it's positive and you multiply it by itself, it will be a positive. If it's a negative multiplied by itself, it will be a positive. So there is no number when you square it that will equal a negative. Okay? Keeping in mind, if you try to do negative 2 and square it, it gives you a positive 4. So negative 2 is not going to work there. And obviously positive 2 squared isn't going to give us a negative 4. It also will give us a positive 4. So once again, if no matter what we plug in for x, if we square it and then add 4, it will never equal 0. Therefore, our domain, once again, is going to be all real numbers. Okay. All right, so that's everything we need to know about domain with rational expressions. Now we're going to actually look at reducing them, like a fraction we would reduce, and some operations with them, adding and subtracting, multiplying, dividing. So first we're going to recall how we can convert fractions and reduce a fraction. Okay. So, because if we relate these crazy looking fractions to just basic regular fractions, it helps us to know how we're going to handle them. So keep in mind, if we want to rewrite a fraction with a negative denominator, because that's something that we're going to be asked to do in this section, a little confusing, but we could take any fraction. So in this case we have the fraction 2/3, and we could find an equivalent fraction by multiplying a top and bottom by whatever we want. So if we wanted to make this fraction have a negative denominator, we could multiply it in the bottom by a -1. But if we do that with a fraction and we still want an equivalent fraction, we always have to multiply the top by the same value. So saying 2/3, if we multiply top and bottom by -1, 2/3 is going to be equivalent to -2 over -3. Okay? So -2 over -3 is the same thing as a positive 2/3. So that's something where it's going to come into play when we get down here. But then also reducing a fraction, something like 15/20. Okay? The way we probably think of it is what number will go into the numerator and denominator. What factor do 15 and 20 have in common? And if you find one, we can divide it out of each. Okay? But what might be a better way to approach these, with what we're going to have to do down here, is to think, okay, 5 is a common factor to 15 and 20. 5 will go into both. So you want to think of it as, 5 times what gives you 15? So 5 times 3. And 5 times what gives you 20? 5 times 4. And once you see that you have a common factor in the numerator and denominator of a fraction, you can divide it out. So this fraction is going to be equivalent to 3/4 once we divide out the common factor of a 5. So this is important. When you have a common factor, something that's being multiplied in the top and in the bottom, you can divide it out. Okay. So, rational expressions use these same rules. They just look a little different. So if we want to find an equivalent fraction to the one that we have right here, kind of like we did up top here. Let's say we want to have an equivalent fraction where this bottom c value is a positive. Well, the one way we could do that is by multiplying the top and bottom of that fraction by a negative. So we could take this fraction and multiply by -1, which is going to change these two signs. But if we want an equivalent fraction, we'd have to multiply the top by a -1 as well. Okay. Doing so is going to give us, right here, a -c and a +6 up top, and a +c and a -5 down below. Okay. And then you might even see that written as 6 minus c up top and c minus 5 down below. Okay. So we could do that, and this expression right here, this fraction, is equivalent to the fraction we started with, but now we have a +c down below, and now it's a -c up top. They look, a little bit different. Things look rearranged, but technically they're the same because we multiplied by the same value, top and bottom. Maybe a little more important and useful skill is going to be reducing fractions, writing them in what we call lowest terms. So we're going to look at that now. So reducing it, we can do just like we reduced the 15/20 above. We look at our expression here, 8k over 16, and we see, do we have a common factor? And we can look at just the numbers and determine that on this one, we do. Okay. Well, you want to find the biggest factor that's a common, and since 8 goes into 16, 8 is going to be the largest factor that's common to the top and bottom. So we can rewrite 16 as 8 times 2. And then it's pretty clear to see they both have a common factor of 8. We can divide that out. And this expression is going to be equivalent to saying k over 2. Or another way to write that would be 1/2 k. Either of those two are correct, though. Okay. So that's how a lot of these are going to work. If we have a common factor, we can divide them out. Well, looking at this next expression, we have 12y parenthesis y plus 6 and 20y squared parenthesis y plus 6. So right off the bat on this one, we see we have a common factor. The y plus 6 and a y plus 6. We can go ahead and divide those out because it's common. It's its own factor whenever it's in parentheses like that. So then what's left is we have a 12y and a 20y squared. Well, we can look at the 12 and the 20 and think if they have a common factor, and they do. Both 4 will go into both of those, and it's the largest number that will. So we can think of 12 as 4 times 3 times a y. And then the 20y squared we can think of as 4 times 5. Then we have the y squared, which we could break that down even into 2 separate y factors, y times y. So now cutting through here, we could divide out any common factors. The 4's will divide out, a y will divide out from the top and bottom, and then everything else won't divide out because they're all different factors that's left. So we're left with a 3 up top, a 5 down below, and a y down below. So 3/5 y, or 3 over 5y. Okay. So those two both were kind of set up decently for you. The next example, 7a minus 14 over -a plus 2, is going to be a little more difficult. With all of these problems where you have expressions like this, we want to try to factor if possible. Okay? So we actually should be able to here, okay, factor out a GCF. In the top expression, 7a minus 14, we could factor out a 7. This is going to give us 7 parentheses. 7 times a gives us 7a. 7 times negative 2 gives us minus 14. All over minus a plus 2. So if we factor out the GCF, in that case it was a 7. Okay. So now, do we have a common factor, top and bottom? Whenever, if you don't have anything in your top and bottom, or if you don't have anything and it's not factorable, you can essentially write a parenthesis around your whole denominator or your whole numerator if it was like that. But we don't have the exact same factor here. We have an a minus 2 and here we have a minus a plus 2. They're almost identical. They're just off by the signs. See how they're opposites? A is positive, here a is negative. Here 2 is positive, here 2 is negative. They're both off just by the signs. Well, when you have opposites, you want to factor out a negative 1, and then that's going to make them be the same factor. Okay, so let's write that in. If you have opposites, we want to factor out negative 1. So up top we had the 7a times the a minus 2. Down below, if we factored out a negative 1, well, a negative 1 times a positive a would give us the negative a we had there. And then a negative 1 times a negative 2 would give us the positive 2 we had there. Now you can see we actually do have a common factor. A minus 2, a minus 2. Those will divide out, leaving us with 7 over negative 1. And well, now we can reduce that. Any number divided by 1 would just be itself. So any number divided by negative 1 would just make it negative, whatever it itself is. So 7 over negative 1 would give you negative 7. Okay? So with any of these problems like that, you're going to want to factor your top and your bottom in order to see what's going to drop out. Okay? It's very common of students will come here and try to cross out the a's, thinking that that's a common factor, or do 14 divided by 2. It's not going to work like that. It has to be a common factor. 14 isn't a factor to the top. It's being subtracted from 7a. If you had a 14 out front that was being multiplied by the whole top, like we had up here a 12 being multiplied by the top, or 20 being multiplied by the bottom, that's different. Here the 2's being added to the a, and here the 14's being subtracted. So we always need to factor things first. I guess what really we'll demonstrate is that is this next example. 5x plus 12 over 5. I have a lot of students that will take a problem like this and think, okay, well the 5's are going to divide out here, and that's going to leave us with an x plus 12. Okay, that's not the case. We have to be able to factor out this top, and 12 would have to be divisible by 5 in order for 5 to be a factor of the top. So it would have to look something like, if it was 5x plus 10, and we could pull the 5 out and open up a parenthesis and write it as x plus 2, then we could divide 5's out. But that's not what we have. So 5 would have to divide 12 in order to reduce. So because we can't factor the top, the bottom, we can't divide a 5 out of top and bottom since 5 is not a factor of the top. Therefore, we look at this and we say that it is fully reduced. So there's nothing to do in this problem. We have to just keep it how it is. Okay. Going to the next example, we have x cubed minus 27 over x minus 3. The bottom, clearly that's not going to factor, there's nothing to do there, so we can think of it as its own factor of x minus 3. The numerator, however, we would need a factor, and it's one of those special cases we learned of in 6.3. It is the difference of two things, so it looks like maybe difference of squares, but it's not squares, it's cubes. We have x cubed minus 27. 27 is a cube, so that is going to be the difference of cubes. So let's write this down. The formula for that. And remember, the way we remember that little acronym is SOAP. Same, opposite, always positive. So the formula for the difference of cubes was when you have something to the third power, or cubed, minus something else to the third power, something else cubed. It's going to equal, well, here the same sign goes in the first parenthesis, so it's going to be box minus triangle, parentheses, square whatever the box is, and now O for opposite sign, so it's going to be addition here, and then this middle term is going to be your box times your triangle, and then the last piece, the last term is always positive, so it's always going to be plus the triangle squared. Okay? So we just want to look at our problem and think, what are we squaring in the first term? Well, we're squaring x, or sorry, what are we cubing? We're cubing x. And what are we cubing to get 27? Well, we're cubing the number 3, because 3 cubed will get us 27. So we have x is our box. Okay, that's what we're cubing to get x to the third. And 3 is our triangle. That's what we are cubing to get 27. So following the formula, box minus triangle, x minus 3. Box squared would be x squared. Plus box times triangle would be x times 3, or 3x. Plus triangle squared would be 3 squared. Okay? So really it's going to be a x squared plus 3x plus 9. Okay? So we can take this now and writing it in factored form. We have the x minus 3 times x squared plus 3x plus 9. All over, well, we already had that x minus 3 down below that we can put around our own set of parentheses like we said. Now we see we do have a common factor. X minus 3, they divide out. And so we can simplify this, reduce it now, and it gives us our final answer of x squared minus 3x plus 9. And that right there would be our answer. Fully reduced, we don't even have a fraction anymore. Okay. So that was kind of a tricky one using that difference of cubes, but a lot of these you'll just have to factor using one of the factoring methods we've looked at. Alright, last expression, last problem we'll do in this video. We have 4 terms up top, 4 down below. We can't start dividing anything out until we have these both in factored form. And because we have 4 terms in the top and 4 terms in the denominator, we want to use the grouping method of factoring. Okay. Grouping is where we group our first 2 terms and our second 2 terms. And then we want to do that with the denominator as well. Group the first 2 terms and then group the second 2 terms. So we want to take a look and see, what do we have in common? Well, of our first 2 terms, they both have an r, so we can factor out an r, and that's going to leave us with a p plus q. Because distributing back would give us rp, or pr, and then r times q is the same as qr. Plus, we can factor out here, both of these terms have an s in them, so s times p would give us ps, and then s times a positive q would give us qs. Okay. So there's our numerator. Now we have to factor the denominators. Both of these terms have a p in them, so factor out the p. And leaving us with a p times r, give us pr, minus p times s gives us the minus ps right there. And then last grouping here, we have both of these terms have a q in them. So we can factor out a positive q. Q times an r gives us qr. Q times a minus s gives us minus qs. Alright. So the last step of grouping is, well, we have the common binomial here and the common binomial here. So we can write this as r plus s, the two GCFs we pulled out, stick them together, times the common binomial p plus q. Down below, we have the common binomial r minus s, which is good. So here we can put the two p and positive q together, our two GCFs, times the common binomial r minus s. So very last thing to do now is to finally reduce it. Do we have common factors in the top and bottom? We do. We have a p plus q factor here and a p plus q factor there. We can divide that out. Alright, so what do we have left? It's going to be up top we have an r plus s over, down below we have an r minus s. And you might think, okay, this is like the opposites where we could factor out a -1 to make a match, but it's not true because here they're both positive and here the r is positive but only the s is negative. So even if we factored out a -1, it would make it a negative r and a positive s, and they still wouldn't match. So these aren't really completely opposites. So that would be our final answer. They're not opposites. We can't factor out a -1. So this right here is fully reduced. Alright, and that is everything that we'll get to in this video. There will be one more video to finish up section 8.1 to handle the multiplying and dividing the fractions.